All right, so hello everybody and welcome to our new Raspberry Pi Pico class. I'm going to remove these headphones for now, but I will put them back in the Q&A session. This will be a good opportunity to charge them while I'm speaking. During the class itself, just use the chat to ask any questions, and we are going to have 1 hour for class and then 30 minutes of Q&A session. Hi, I'm Wokwi, and I'm here to share with you some of the knowledge that I gathered about the Raspberry Pi Pico. And before we get into all the details, let me just share with you a link to a document, and I will use this document throughout the sessions to share links and information with you. And it's like a collaborative document, so you can also comment on it. You can write where you are from. So this is our Frela, the Raspberry Pi Pico. You can already see I connected a few debug probes to it. We are not going to use those today. Actually, I think we won't be using the hardware today because I've got something else for you. We are still going to talk about the Pi Pico, don't worry. You didn't get into the wrong class, but we are going to use an online emulator. I know just hey, Alexander hey, Alexander, I think you also took part in the AVR class, so good to see you here again. Anyway, let me share my screen and let's start rolling with this new fella. And while I'm at it, just let me know if you can see my screen now. Hopefully you can, and I will open the chat so I can see any questions and comments. 2 Brazilians already and 1 from Turkey. Cool. So this is the document, and one fun fact about myself before we get started, I'm also a salsa dance teacher. So if you want to dance salsa later, let me know. Thanks for letting me know that you can see the screen. So in this class, we are going to do most of the practice in an online emulator that I'm working on. So this is the emulator. It's called Wokwi. This is a project I have been working on for the last year and a half or so. And this is an Arduino emulator. But since the Pi Pico came out, I was really intrigued, and I decided I wanted to try to create an emulator for it as well. So that's what I've been doing for the past 3 months over a live stream. I'm live streaming those coding sessions where I'm working on the emulator. And this is also how I learned about all the internals. Now, this is a brand new board, and I try to learn as much as I can, but as you will see, there is a lot of information to ingest, and I'm still not an expert. I'm still working on it, but I would love to share with you whatever I already know, and then we can, if you have any questions, I will be glad to look for the answers together with you and find them together. So this is the simulation environment, and you can see we have a Pi Pico here, and I'm using the Arduino core for the Pi Pico, and this is super new, so it lets you use the Arduino environment. So if you are coming from Arduino background, you can see like pin mode, digital read, digital write. It's basically Arduino code, but the Arduino core lets you run this code on Raspberry Pi Pico. So let's just start with the simple blink, and you can see we have an LED here. It blinks. And I think the cool thing about writing this in the Arduino environment using the Arduino library functions is that we can easily swap the board. Let's say we will swap it to Arduino Nano, and you will see that the same code still blinks the LED. And other than this code editor and this diagram, you can see there is also this small JSON file that defines the parts and the connections. And right now there is also, let's change the code a bit, go back to the Pico. There is also like this thing where we can just add components from a dropdown. This is new, so there are bugs. If you find them, I will be thankful. So we can add an LED, and you can see it created the two connections. And then we can just, change the code to blink that LED, just so we can see how it affects the, now it blinks this LED at pin GP1. Gwen is asking whether the simulator is open for everyone, and the answer is yes. And actually, this is the first resource I'm going to link on PyPico. I'm going to share with you in this document, so you can also start playing around with it. And I must say that I worked really hard today to get it to a usable state. So there are probably some bugs in the PyPico emulation. I literally worked all day, so we can use this today in class, and you will be able to run these examples. Oh, I skipped. Now I spoiled the next example. You will be able to run these examples even if you don't have the PyPico, but there are probably some bugs, and you will see a lot of changes in this emulator until we get to the final class. A link for Google Docs. So this is the link. I will copy it again to the chat in case someone missed it. And keep this link because we'll use it in the next classes as well. All right. So the first thing I want you to know about the simulator, we still don't have USB, and by default, the Arduino core uses USB for debug print. So if I will do this, you're probably using it, not serial. You're probably used to it from Arduino, where you use the serial terminal, the serial monitor to print debug output. It doesn't work because by default this uses USB, and this would work over physical Pi. But if you wanted, if you want to use the serial monitor in the simulator, you can just use serial 1. And serial 1 uses the hardware serial that is wired to this GP0 pin. You can see that I connected it to this virtual serial monitor. And now if we run the code, you can see that we get the output. So the first thing I want you to remember, and I forget it all the time, so remind me if I forget, please do, is that we need to use serial 1 for now in the emulator. Probably in a few weeks, we'll also have USB, and then you will be able to use serial whatever as well. And now that we are able to print things, let's start our journey. Let's meet our friend for the next few weeks and my friend for the past few months. The Raspberry Pi, the RP2040 datasheet. And the RP2040 is like the chip at the heart of the PyPico. It's a new silicon they developed. And you can also already see it's like 647 pages. This is enormous. And before we dive in, I just want to, I mean, we won't read it, all of it, but I will show you how I approach reading data sheets for new chips or microcontrollers that I want to get familiar with. But before we do this, let's just make sure that everyone is on the same page with bitwise operators, because we are going to use them a lot in this course. So I think I posted a link in the course page. So if you go to the course page, there is like a guide. But I think just to make sure that there is like this notation that lets you write a binary number. So let's say value and specify the bit. So this is how we can write a value in a binary, so zeros and ones in Arduino. And if we wanted to convert it to a decimal value, we can just serial println, and we would see the decimal value, in this case 128. And then we can do the opposite as well. Let's say we have 42, and we can ask Arduino to print it as binary. For some reason, it doesn't. Oh, yeah. Okay, and then compile, and then we can see this is like 101010. So this is a quick way to convert between decimal and binary in Arduino. And also there is this useful bit macro. So if I use bit 8, then you will see it returns a number where the 8th bit is set to 1. It's actually the 9th bit because we are starting from 0. And then I can also bitwise OR with bit number 1, which is the 2nd bit from the left. Again, we count from 0, and we get those 2 bits on. So just to make sure that everybody is sort of familiar with these syntax, and if you tend to forget about the bitwise operators, there is a nice blog post here. I will also put a link with like those GIFs that help you remember how all those operations work, like XOR and OR and everything. Where was that? Bitwise GIFs, just for the sake of it. And now that we know about bitwise, I mean, you should have probably read this before and understand. But if you have any questions, then feel free to ask me in the Q&A session later. Let's start diving into the documentation. And usually when you start working with the Pico, you won't dive right into this datasheet. There is another nice getting started guide. We just tell you how like to set up things on your computer and how to set up the SDK and how to program it and debug it. And my goal with the emulator is to save you all of this. So of course, if you have a physical hardware and you want to do it, then yeah, I encourage that. But if you just want to, practice and you don't have access to the hardware itself, then you can basically skip this getting started guide for now and dive right into coding. So this guide doesn't really explain about the board or the chip too much, just the basics, but it tells you how to set up and how to build stuff, and see, it's very detailed. So we're not going to need it today, and probably not going to need it. Maybe I will tell you to look at it if you want to do this or that, but we're not going to use it. We are going to use this guide, and this guide is like almost everything you need to know about the chip. And I say almost everything because around class number 3, we'll open another datasheet that has information about the ARM instruction set, but we'll get to that. So first of all, I find this fun fact. It's not really important, but this tells you like how the part number scheme works. So you can see it has 2 cores. They are Cortex M0, so that's the 0. That's like the amount of RAM it has, log RAM divided by 16K. And then that's like the amount of flash it has. It doesn't have any flash built into the chip. The flash is always external, so that's why this is 0. So this might be a hint that they are going to release other processors with different amounts of RAM or flash or different kind of processors. And maybe not, I don't know. Anyway, usually when I open a new datasheet, the first thing I'm looking at is this summary, and it doesn't give too much information, just very high level overview. You can see like how much RAM you have, how many GPIO pin. So we have like 30 GPIOs, but then we have 6 other GPIOs or IOs for the SPI flash, which we can also use as GPIOs in certain situations. And then I think there is like 4-channel ADC analog to digital, and probably if they had a digital to analog, they would also mention it there, but they don't. And USB 1 host device. So I usually read this section if I'm comparing a few chips and I want to find which chip is best for my needs. But in this case, we already know, I mean, you are in this Pico course, so there is no choice. We are going with this one. And then after this, I usually start in, I look for memory address map. So this is where I like to start exploring datasheets. And you can see like there is, there are a few sections that in the memory space of the Pico, there is this ROM, there is XAP, which is a weird name. We'll explain that in a moment. SRAM, so that's the RAM where your variables are stored. And then a bunch of peripherals, registers, and internal registers, which we will get to. But first of all, where is our code running from? So one way to answer that would be to read the datasheet. I mean, I would guess it might be from the ROM or from Flash, but I don't see any reference to Flash here. But in this case, we can also use code to answer this question. So let's just print the value of setup. And I think printing it like that would probably not work because of, of type issues, but we can probably convert it to unsigned long int and then print it as hexadecimal. And yeah, we can see that this is the address, the memory address of setup. So now we know where setup lives. And let's also see, I mean, we already know like, where was that? In the datasheet here. We already know that the SRAM is mapped here, but let's just make sure, let's just print the address of like, let's say this value variable. And then we should, yeah, we can see that int value lives here. So yeah, so now we know that this is, I mean, we already knew that this is the SRAM, but now we can see it in our eyes, and we can see that setup belongs to this XAP. And XAP actually, when you click on it, you don't get a lot of details, but when you click twice, it says that this is the flash, the external flash, and there is a memory window starting at this address that whenever you read from, this is translated into a serial flash transfer. So that's basically a fancy way to say that the external flash is mapped in this address, which we can see here. So this is like where I like to start, just so whenever I see an address, a memory address of something, I know where it belongs to. And then there is also this ROM, and the ROM is just 60 kilobytes of read-only memory, and they are like, it's fixed, it's hard-coded in the chip. You can't change it, and in general, it just it takes care of booting the chip and letting you upload new code through USB. And there is like this link, which I really like. This is the source code of the flash. So for most chips like the ESP32, they also have built-in ROM with some code, but you don't get to have the source code. And here you have the full source code, which I think is really cool. By the way, let's add this data sheet. Oh, somebody already did. Thank you. Yeah, thank you, Patrick. I already added it now, but thank you for, yes. All right. And yeah, the built-in UF2 support is awesome. It means that you can just plug in this PyPico and drag a file into it, and it will program the Pico. You don't need to install anything, just plug and play. Amazing. And if you are interested, you can, what was that repo? You can find the source code for that bootloader here in the boot ROM. You see there is like this USB boot device, and probably there is an external library that takes care of the UF2. But anyway, we'll take a look at the boot ROM in one of the next classes. I don't want to dive too deep right now. So we have this boot ROM, then we have the flash, then we have the SRAM, then we have this APB peripherals. And if we click here, we can see that there is like a bunch of peripherals with strange names. And we'll go over some of them today. You can see that we have SPI, UART, PWM, analog to digital, I2C. Somebody is asking for that link again. So yeah, let's post it again. I2C. So basically, these are like all the peripherals, and they are mapped to this address space starting with 40 million. And next there is, next there is like AHB light peripherals. And you're probably asking yourself, what are those APB and AHB light? These are just types of data buses that are part of the ARM specification. And we don't really need to understand the details in order to use them. And you can see that for the AHB Lite, we have DMA, and then also the USB and the PIO, which is a cool feature of the PyPico, the programmable I/O. We'll use it in the last class. And then we also have SAO base, and we are going to talk a bit about SAO today. SAO is single cycle I/O block. And don't worry about that. We'll explain it in a moment. And we also have a bunch of internal registers that are part of the ARM Cortex-0 specification. And we are probably not going to talk about them until the next class. All right, so we have this address map. Now, if we see a memory address, we know how to look it up and see where it belongs. And another interesting thing to look at is this bus fabric, and it's a bit complicated, I guess. There is a lot going on here, but basically just showing the connections between the various parts of the systems. So you can see there are like two cores, two processors that are connected to this AHB Lite crossbar, and they can use this fast bus to access the ROM, the SRAM, the flash, and also through this splitter, this PIO, and USB. And there is also an external DMA controller, which lets you transfer data between the memory and some peripherals. And it's also connected to this fast AHB Lite bus. And then there is also another bus, which is the APB bus, and all the peripherals are connected through this bus. So basically, as I understand this it means that those ones get the microcontroller, the CPUs get fast access to those ones at the top, and those ones go through the splitter, so they get slower access. And we could go into the details, but like it explains how it works and how you can get um, um, like the bandwidth that you could get, I think up to 2 gigahertz. But usually, yeah, up to 2 gigabit per second. But for the most part, this is just to give you good idea or basic idea about the connections inside the chip. I don't think it's super useful unless you need to do something that has a very precise timing requirements. And if you do, there is like a bunch of registers that help you figure out these registers perf cell, like let you monitor the performance of accessing peripherals through these buses. But again, not interesting right now. Cool. So there is also like I think there is like this diagram of the chip, which shows another like block diagram of all the parts in the chip. I don't know. I don't find it very useful, but it's, again, if you just want to get a quick overview of what peripherals you have and the connections inside a chip, SWD is like a debugger interface. All right, so I think that's what I usually try to, when I get a new datasheet, a new chip I'm looking at, that's usually what I'm starting to look at, like the memory addresses, how the peripherals are connected. And as we will soon see, there are like some very interesting details hidden here, because what we see here is that what we have seen so far is just like the high level connections, but there are like interesting things like this atomic register access, and we'll get to that in a moment. But before we get to that, let's talk about GPIO. So we have this setup where we blink an LED, and I created another setup here with that's the same code other than the LED number, and you have 8 LEDs. And this is like a great example of where Arduino sort of kind of limits you, because Arduino provides you an API to write or read from a single pin. But what happens if you want to write to multiple pins at once? For instance, what happens if you want to blink all the LEDs? So sure, you could do some kind of for loop that would iterate over the LEDs, but I mean, that wouldn't be very efficient, and that's also a lot of code to write. And this is where knowing the actual hardware interfaces of the chip really starts to pay off. So let's see. How do we access the GPIO, not through the Arduino library, but rather through the hardware, the registers? And whenever we want to access the hardware directly, we have to look for those registers that control that specific piece of hardware. And usually inside most of the chips, there is like a GPIO hardware peripheral, and you can see there is one here that explains how to use the registers, how to write to specific memory addresses to control GPIO. Specifically in the Pi, you can see that there are like a few ways to control the GPIO. So there is software control via SIO, single cycle IO, which we are going to look at right now. And then there's like all those peripherals that can also access the GPIO and control it. In addition to that, there are like 2 banks of GPIO. There is like the user bank, which is like the standard 30 GPIOs. And then there is also like the QSPI bank, which is like a bunch of 6 GPIOs. It's probably written somewhere. 6 GPIOs that are connected to the flash chip on the Pico. So in our case, we are not interested in controlling those. Those are like used by the bootloader to see if you press the boot cell button. But other than that, I guess they are not very useful for user code. Rather, we are going to focus on this user bank with GPIO 0 to 29. And we are going to use the standard interface, the software control interface via SAO. So let's take a look at that. And we can see that there are like 2 identical set of registers that control the GPIO. There is like GPIO X for direct control of IO bank FS0, which is like those user GPIOs, and GPIO high, which is not interesting because it controls these GPIOs that are connected to the flash. So not interesting, and this one is interesting. Somebody says that he hopes the clocks aren't as annoying as the sounds. Atmel has a tendency to make very annoying clocks. Here the clocks are quite simple, and we'll take a look at them in a few minutes. Cool. So if we want to control the GPIO and like the output, there is like a GPIO ART register that allows us to do it. And it sets the level of a GPIO 10 high low. So this sounds like a good candidate. And if we check it, we can see this is the register, and we can see it has out of 32 bits, there are like 30 bits from 0 to 29 that are relevant, and then we can read and write to them, and we can use them to set the level high-low of each GPIO. So basically, this is like a single register GPIO out that we can write to and use it to set the values or the levels of the GPIO pins. And this is the offset of the register. And if we go to this, so it's relative to the SAO base. So let's define it for a moment in our code. GPIO out. And then we can add those 2 values. Const unsigned int. Actually, we can just add them like that. So that's the SAO base offset plus the register offset. And then actually it's a pointer. And then we know that we can, by writing to this address, it says that we can control the output of the GPIOs. So hopefully, if we write there all bits once, like 8 bits of once, it will set all those like GPIO 0 to 7 to high. And then if you write there 0, it will set all of them to low. And it doesn't build because we need a typecast because it's a pointer. Okay, and let's run it again. And oh, it's not const. Oh yeah, we need to write at the address this is pointing to. So this syntax means write at the address that is stored in this variable. All right, and now it's almost working. Only one LED is blinking. And do you know what is the reason for that? The reason for that is that we haven't set our LEDs to output, so only one LED. If we set another LED, we can see, or I think this one specifically doesn't work right now in the simulation due to a bug. Okay, that's interesting. I promised you there will be some kinks, and here they are. Yeah, for some reason, those two don't like to work. But yeah, other than interesting, all the even ones don't work. That's I will have to some fun debugging this tonight. Anyway, this is like one way to control the GPIO. We can use it to set a bunch of pins, but just like we can control use this to control like the values of the GPIO, there is another register which is GPIO out enable OE, which allows us to control the oh, wait a moment. I think I may have some idea why it's not working. So let's a plus. Yeah, the funny thing is I tested all the examples, but then I uploaded a few changes to the emulator, and now yeah, IntI, writing too much JavaScript. All right. Yeah. Okay, so interesting. All of them works other than 0, maybe because 0 is connected to the serial monitor. It's not working. But if we cut this connection, still not working. Okay, I will have to debug it later. But anyway, you can see that by writing to this register, we don't have to do this loop where we set each LED, each pin individually. Even more, instead of like having to do like writing ones and then zeros, there is another register in this GPIO SAO GPIO section, which you can see here. So other than the out, there is like a register that allows you to set or clear a specific bit or a specific pin. So you can use it to control a specific pin. And then there is like another one that lets you XOR them. So toggle one of the pins, and you can, that's the offset of it, and you can write a value to it, and writing the value will just toggle those pins. So for instance, I can do something like this. Let's change this to the GPIO out toggle or XOR, and then I can just write this value, and it will just toggle them for me. So I don't have to other than 0. Maybe that's just a defective LED and I have to replace the LED. I don't know. So that's another cool shortcut. So I could do something like, if I wanted to have a nice pattern, I could do something like, let's have this GPIO out again, so we can set a bunch of, that was 10, right? GPIO out is 10. Yep. I can set a bunch of registers, and then I can do something like that to have this fancy pattern. So just, yeah. Oh, I don't want to toggle those. I just want to set this pattern. Yeah. Okay, interesting. Yeah, so Mark is asking how to add registers, and right now, if you want to add them to the simulation, you can do it through diagram.json, but you can really skip them. I mean, there is no, yeah, we'll link that sketch, of course. 8 LEDs sketch. Cool. So yeah, so these LEDs are simulated ones. They will work fine without these registers. They are just a decorative thing. There is no analog simulation, so they are just, in the simulation, they are just functioning as a wire. They have no function. All right, so yeah, we can see there is probably some bug that I have to figure out in this GPIO out mechanism simulation, but ideally that would just create like half of them would start on and then they would all blink. So I promise to fix that bug for the next session, and then you can try this example again. And just like the SAO allows us direct access to the GPIO pins to get output, the other direction is also possible. So we have a bunch of input registers. So if we go back to the SAO, you can see we have this out and outset clear store. And then we have a bunch of those to set a pin direction, whether it's output or input. And then the highs aren't interesting, but there is also GPIO in, which we can read from to read a bunch of GPIOs at once. So let's try to do that. We have this demo with a bunch of switches. And if we start this, it just has the setup. It says those switches are connected to these GPIO pins 8 to 15. The reason is that this pin is used by the serial terminal and we don't want any conflicts. And then we can, just copy this. I think it will work with the const now that I'm using it as a pointer. So we said the offset is 4, and that's, let's call it the same name as in the datasheet GPIO in. And then I can just, print the value of that as a binary. So, yeah, maybe this is already defined. Yeah, I guess it's already defined for some other purpose. So let's call it red GPIO in. So we don't have any conflicts. Oh yeah, we need to read this value, not past the pointer, but the value. And yeah, you can see it's 0. But now if I change, let's add a delay so I can change it and see it changing. So you can see as soon as I toggled, interesting. Oh yeah, I know what's going on here. I need to enable the pull-up resistors on this pin. So 8i less than 16i plus pin mode. So that's the Arduino way to enable pull-up resistors on this pin. And now, yeah, you can see like whenever they actually go to 0 when I change them, because and yeah, you can see like Arduino doesn't print the leading 0, so it's a bit confusing. But then if I just want, to print those only those values, I can shift it by 8, so we don't get those lower 8 bits for those GPIOs that are not connected. And yeah, and then you can see like let's disconnect them all, so it will be 1 1 1 1 1, and then we can just play around with them and see the result. So that's basically how we use registers to access the hardware. And instead of like doing pin mode and all of that, there are also registers that control that. So for that, there is like a bunch of other registers, not a part of the PAO of the SAO. There is like a GPIO peripheral, and they're like you can see here for each GPIO, there is a control register for each specific pin that lets you set up what this pin is doing. And the important part here is that you can select different functions for each pin. So for instance, there is a table here somewhere. Yeah, here. Yeah, so you can see each pin has a bunch of alternate functions. And you can set that register that I just showed you, GPIO 0, 1, etc. control, to select which peripheral the pin is connected to. So that's how you choose, you associate pins with peripherals. So for instance, if we look at this GPIO 0 CDRL, we'll probably see it set to 2 because the UART is enabled on that pin. Let's try that. Where is what's the offset of it? This is at offset 0, at offset 4, sorry, from this is like the base of the IO peripheral. So let's have this register GPIO 0 control equals this plus 4, right? Yep. So now if we read from this, we expect it to be 2 because this pin is configured with the serial port. So yeah, we can see, let's remove those prints for now. Yeah, we can see that the output is 2, and this is connected to the serial port. And if we choose another pin, for instance, let's say pin 8, let's change this to 8 and add another one for pin 8. Where is pin 8? Pin 8, where are you, pin 8? So that's 44. 44, yep. It should be 5, and I will tell you why in a second. So this pin is now set to function number 5. And if we take a look at the table, we can see that function 5 is SAO. So whenever you want to control the pins directly as GPIO through software, you just set a function to 5. And then if you want to connect them to a different peripheral, then you can set the function accordingly, like the UART in this case. So that's one more way, or one more memory, a set of registers that control the GPIO. And to make things a bit more complex, there is even more. So other than those, there is also like a set of PED registers. And PED registers are how you enable things like the pull up or pull down resistor, and you can also set like how much current these pins can supply between 2 milliamperes and 12 milliamperes, and other like parameters like disabling the output for the pin altogether. And there is like here is what those registers look like. So for instance, if we wanted to implement input pull up ourselves, we would need to set this pin in GPIO 0 bank control register and this bit. And let's do that. But instead of like having to, usually if we want to set a bit, we need to read the value of the register and then set a bit and then write the value of the register. But the Pico has a nice feature that allows you to write, like to set a specific bit in a specific register of a peripheral without reading the value first. And let's see how that works. So if we want to set pull down, for instance, we want to set bit number 2. So that's the PED bank. Let's say we want to do it for, let's do it for PED GPIO. What is that? PEDs bank 0 GPIO 8. So that would be 24. 24, that's the address of the PED control for this register, and it's relative to this PED control peripheral. So yeah, so that's the address. And yeah, and then we can like do this by, you know, using, there is an Arduino macro for that. To set bit number 2, I think. And that's, what doesn't it like? The expansion, assignment of read-only location. Oh, probably because we have this const here, I guess. Yeah, so that's one way to do it, to set this bit of the register, but behind the scenes, this means that we need to read the register, set a bit, and write it back. But there is another way which works across all the peripherals, and that's one pretty nice feature of the Pico. I told you about it a few minutes ago, and now we're getting back to it. It's called atomic register access. So for all the peripherals, if we added a specific offset, we can, instead of writing to a register, we can do something else. So if we had 1000, we XOR those registers. 2000 would set the bits that we assign, and 3000 hexa would clear those bits. So in our case, we can just, add 2000 hexa to the address, and then all we need to do is just like set it to a value with a second bit set, and that would just do the same. And yeah, actually, we don't really see it, but it did the equivalent of setting pin number 8 to pull up. Maybe we can enabling the pull up on it. Not sure if this will still work. Yeah, you can see like now the pull up for this pin still works. Like this is the one connected to pin number 8. Oh yeah, of course it works. We call it pin mode. Yeah. Okay, great. So now it doesn't work. And I think the reason it doesn't work is if you check out these PEDs, what was that? The PEDs, GPIO, and then we had that link to the PEDs somewhere here. Yeah, if you check out the register, you will notice that by default, the pull up is not enabled, but there is a pull down that is enabled. And and we actually enabled the pull down as well. We set bit 2 and not bit 3. So first of all, we want to set bit number 3, right? And then I think that wouldn't work as well because we already have like the pull up. Oh, wow. This made the simulator go crazy. Setting up pull up and pull down at once probably isn't a very good idea. But let's see what happens if we just, instead of setting this bit, we use the other register, atomic register shortcut to, XOR. So we are going to switch bit number 2 off and turn bit number 3 on at once. No. Oh, I know why this probably doesn't work. It probably doesn't work because let's see the print at the beginning. Yeah, you can see that now that we haven't set the pin mode on that pin, on pin number 8, then it doesn't have a function. The function is 31. That means it's unassigned. So let's set a function to 5, which we have seen above. 5 is like the SAO function select. Yeah, 5 is SAO. So now I think this should be the equivalent. And this is not const anymore. GPIO 8 control. Yep. Okay. And now we can see, I guess, that, function is number 5. And let's clear the terminal. Oh, why did we remove the delay? I think that wasn't a wise thing to do. Okay, and now, still doesn't work. Interesting. Anyway, yeah, you see, I still got some work to do on this, on this simulation. But what I wanted to show you here is that we have a bunch of hardware features like this atomic register access, or those this ability to write to multiple pins at once using the SAO, or read from all the IO pins at once using the SAO registers. And these aren't available if we are just using the high-level Arduino libraries. And the truth is, you don't really need to write all this code if you want to access this. This has already been done for you. There is a great SDK from the Pico, and it has a bunch of functions like GPIO set direction, GPIO set function. So instead of like doing this, I can do something like this, GPIO set function, and set a function of pin number 8 to, I don't remember how it goes, GPIO func SAO. So yeah, so that's another way to, just set it to 5. And the nice thing about this SDK is that it's also open on GitHub. I will post the link here. And let's also post the link to these 8 switches. Let's call it 8 switches sketch. Cool. And then that's the Pico SDK. But let me show you a cool trick. If we really want to explore this SDK, we don't really want to do it with the GitHub interface. So you can add 1s to the link, github1s.com/ the rest of the URL stays the same. So I'm adding 1s here. And as soon as I do that, I get Visual Studio Code in my browser that opens this repository with all the files. Let's zoom in. So yeah, that's a very cool shortcut I use all the time. I will just add a link as well, so you will have it later. GitHub1s. And then I can actually find the source code like gpio.c, or I think this one is the right file, GPIO. Here we go, GPIO set function. So we can see it actually calls this, it's writing to, there is like a pointer here, and it writes to one of these ped banks, offset GPIO, which is the same register, and then it enables the input bits, and then it sets this control register to the function that we have passed. So basically this is writing to the same register. So and if we open it with proper, so this doesn't really support C++ code very well, but if we open it with proper Visual Studio Code, that was GPIO.c. I think that was this one. Set function. Yeah. Oh, I got probably a bit older version. Anyway, so if we click on here, we can see all those structs that define those IO banks, the registers, and then all their bits and that stuff. So it's really cool that this is also open source. Cool. And then one more link I want to share with you is this documentation for the Raspberry Pi Pico and Wokwi. So just if you want to use a different, there are like 2 different Arduino cores that you can use. There is like the official one, which is used by default, and a community maintained core. So there's instructions for that. And also this table, which is right now pretty red of the supported features, but over the course of the next few weeks, you will see how it gets more and more green. So this lets you know what is already supported in the simulator. So let's add this here in case you need it. Not the Arduino core, just the main thing. All right, so yeah, apply. And by the way, this has links to the, inside the documentation, there is also links to the source code of the Arduino core for the Pi, the official one, and the school community core. So as I said, this is super like living thing, work in progress. Expect to see updates, new features, breaking things. And I think it's time to switch to the Q&A session. But before we do that, so we will have a Q&A session now, but if you want to ask questions, I'm on this Discord server waiting for you in the RP2040 JS channel. We also have weekly live streams on Tuesday when we hack on the simulator itself if you want to join. There is also the Hackaday chat, so you can catch me there if you need. And just before we switch to Q&A, let me stop my screen sharing for a moment so you can see which the cool shirt that I got in the mail this week. That's the HackadayU shirt. So thanks the HackadayU team for sending me that shirt. All right, let me put on my headphones and let's switch to the Q&A session. Yeah. All right, let me see. If you have any questions, then you can either write in the chat, or you can like just open your mic and ask. And in the meanwhile, while you do this, yeah, Platform IO versus Arduino 2.0. So yeah, so while you do this, let's do one more fun thing until the questions start to surface. So we had this example here where we printed to the serial monitor, but you know, we can do the same with by writing to a specific register. So if we go here to peripherals and UART, then we can just, you know, go to list of registers. There is this first one, UART data register. So if we take a look at this offset of UART 0, add 0, the data register, then we have this, yeah.
Or you might have to share the screen again.
Oh, good call. Yeah, let's share the screen again for this small bonus session. So can you see the screen now?
Yes.
Okay, perfect. So yeah, so I just went to the datasheet and went to peripherals, UART, list of registers, and then the first one is the data register, and basically whatever you write there is written to the UART, and yeah, data receive, transmit, write the character. So you can see that this UART 0 starts at this address plus 0 for the data register. And then, yeah, I had this, started writing something. Okay, yeah, if we take this address, let's call it UART DR, and just, you know, write some value to it, like H, then I expect it to, yeah, it should be a car pointer because I'm writing a character there. Oh yeah, star. Okay, and then you can see that it writes H's. So once you spot the right register, like, you know, you figure out which register you want, you need to use to interact with hardware. It's pretty straightforward, like just writing values to a specific location in the memory or reading from a specific location. So that was just, you know, another quick demo of how to access the other registers directly by the information we have in the datasheet.